Okay, so in this video, we're going to go over section 4.2, which is pages 8 to 12, I think. Yeah, pages 8 to 12. All right. So just make sure you have it out while you're watching this video. Okay, so we're going to go over the differences of the properties of metals, nonmetals, and metalloids, which are 3 different classifications of substances. And then we're going to learn how to draw Lewis dot diagram. So this like new kind of diagram. Okay, so let's start out by going over what a metal is first. So you may have heard of like a metal or metallic substance before. But metals are going to be on the left side of your periodic table. Metals are great conductors of heat and electricity. So this means that they can conduct, they can transfer heat very well, or they can transfer electricity very well. Okay, that's why like all like different like pots that you would cook with or any kind of electrical wires are all going to be made out of metals because they're great conductors. Metals are ductile, which means that they can be drawn into a wire. They are malleable, which basically means they're moldable or can be hammered into like thin sheets, like think of like coins. They're lustrous, which just means that they're shiny, and they typically tend to be solids, except for Hg, which is mercury, which tends to be a liquid, okay, at standard temperatures. Metals will lose electrons when bonding with other atoms, which is super important, which is why metals will tend to have positive charges. So any metal ion, like we can just write a few examples down, like sodium or calcium, magnesium, okay, all of these are different kinds of metals, and they will lose electrons and form these positive charges or positively charged ions when bonding. Okay, so this is just like a picture of all of those things that were in the last slide. So again, they are ductile, meaning that they can be drawn into a wire like this. So this is like a piece of copper metal, can be drawn into a wire. Lustrous means that they tend to be shiny. Malleable, they can be moldable or hammered into thin sheets. So this is like a piece of gold that was hammered into like a flat coin. They're good conductors of heat and electricity. That's why they're used for electrical wiring and for like cooking appliances. They're always going to be on the left side of your periodic table. So all of this that is highlighted in yellow, these are all of your metals. Okay, so most of the elements on the periodic table are going to be classified as metals, except with your hydrogen in group 1 up here, with atomic number 1. Hydrogen is, even though it's over here on the left, that's kind of your only exception. But hydrogen would be a nonmetal, but all of these other guys on the left of your periodic table are going to be those metals. And all those are really going to be solids, except for mercury is a liquid at standard temperatures. Okay, then we have our nonmetals, which are going to be on the right side of the periodic table. They're kind of the opposite of metals, so they're going to be poor conductors of electricity and heat, which in other words means they're good insulators. Okay, so they retain heat or electricity well. Nonmetals tend to be brittle, or they can like break easily. They're going to be dull, so they're like the opposite of shiny, so not very shiny. Your nonmetals are mostly going to be gases, okay, at standard temperatures, except with exception to bromine, which is a liquid. And then your nonmetals are going to gain electrons when bonding with other atoms or when they're forming ions. So if we just wrote down a few examples for these, all of your nonmetals are going to form negative ions. So we can write, like for fluorine, it's going to be a -1 charge. Oxygen would be a -2 charge. Okay, so they form these negative charges or these negative ions, okay, because they are gaining electrons. Okay, remember electrons are negatively charged particles. So if something overall has a negative charge, like this fluorine or this oxygen, okay, that means they gained more electrons. Okay, they added more negative charges to themselves. Okay, so just some more pictures about nonmetals. Okay, so this is just showing, pretty sure the sulfur. So you can see how it's kind of like really breakable. It's brittle. It's dull. It's not very shiny. Most nonmetals are typically going to be gases, with exception to your bromine, which is liquid at standard temperatures. They're the opposite of your metals, so they're poor conductors, which means they're good insulators. So this is just a picture of a wire. So the wire, the electrical wire going through, would be made of metal. Okay, so that's a good insulator because it can carry an electric current through it. However, all wires are gonna have, for the most part, are gonna have like this covering, this insulator covering over top, and that's so it kind of protects us from that electric current. Okay, so this would be that insulator that is a non-metal surrounding that metal wire. Your nonmetals are going to be in this like right section of the periodic table. Okay, not as many nonmetals as there are metals, but there are going to be over here on the right, including your hydrogen that's kind of over here by itself. And then the last category is a metalloid. So these are things that are going to have properties of both metals and nonmetals. So they can be poor conductors, but they may be shiny, etc. So they're kind of like this metalloid. They're like in the middle between a metal and a non-metal. They can have kind of a mix of those properties. So metalloids are going to be in the middle of the periodic table, and they only include these zigzag staircase guys, which we'll see in a second. But these are them listed out. So let's just look at the picture. So you can see here, these are in purple or pink, the metalloids, and they basically separate the metals from the non-metals. And it kind of is along this zigzag staircase here. So metalloids are commonly used as semiconductors. So they're like, sometimes they're like partially conductive, but not completely. So those are commonly used with different electronics like your laptops or your phones. And this is just like a picture of what all of them would look like, right? Some of them are shiny, some of them are dull, so they kind of, they aren't really classified as just a metal, just a non-metal. They're kind of like this in between. Okay, so in terms of increasing metallic character, so the metallic properties or metallic features that elements will have. This is the trend that they follow when you're looking on your periodic table. So as you go down a group, metallic character is going to increase. So for example, if we compare, say, lithium with francium, because metallic character increases as you go down that group, francium is going to be the most metallic. Okay, or at least more metallic than lithium is. But then metallic character is also going to decrease across a period. So see this arrow here kind of goes pointing to the left. So that means as we go to the left across a period, the metallic character is going to increase. So if we compare like two random ones, like let's say beryllium with nitrogen. Okay, nitrogen is definitely going to be less metallic than beryllium, so that trend goes from right to left with increasing metallic character. Okay, so now we're going to talk about this concept called the octet rule. Okay, so oct, think 8. Okay, oct means 8, so like an octagon has 8 sides. An octopus has 8 legs, right? Okay, octet rule means 8 rule. So atoms will gain or lose electrons in order to form a stable noble gas configuration with 8 electrons in the valence or outermost shell. Okay, so it sounds like a lot, but remember how in the previous video, and we talked about how all of these different elements will have a specific number of valence electrons, and these atoms that like to react. So basically anything that is not a noble gas. Okay, remember your noble gases in group 18. Group 18 have 8 valence electrons already. So we say that noble gases are very unreactive because they already have this stable octet. Okay, so everything else that's not a noble gas that has less than 8 valence electrons, they want to react and they want to do something. They want to form bonds with things and react in order to try to pretend like they're those noble gases. Everyone wants to be a noble gas because the noble gases are the most stable. So all of these other different elements or atoms of those elements are going to want to lose or gain electrons, whatever's easiest for them, in order to be most like those noble gases. Everyone wants to be like a noble gas. Okay, so the magic number is this 8. They want 8 valence electrons. But we talked about how metals will tend to lose electrons. Metals lose electrons and form positive charges, whereas nonmetals tend to gain electrons and form negative charges. So if we look at these two examples below, so let's start with the metal first. Over here on the left, we have sodium, which is a metal. It's a group 1 alkali metal. So this is the Bohr model of your sodium. So if we're just focusing on the outermost electrons, though, we only care about the ones that are in the outermost shell. So sodium will have 1 valence electron. It's this guy out here. Okay, so sodium will lose that electron because that's the easiest thing for it to do. It'll lose that 1 electron so that when it does lose this guy, okay, now it will have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so once it loses that one guy on the outside, here, okay, then it'll have those 8 outermost electrons. It'll then have a stable octet. Okay, so that's why sodium will tend to lose those valence electrons in order to kind of mimic that it has a stable octet. So a sodium atom will change, losing that electron to turn into sodium positive 1 ion, okay, where it has a positive 1 charge. And it has a positive 1 charge because it lost that electron. So if we compare it to this other example, is we have a chlorine atom here. A chlorine is a nonmetal on the right side of your periodic table, and nonmetals will tend to gain electrons. Okay, so something like chlorine, which is a halogen, group 17, has 7 valence electrons. So in the red highlighted dots here are representing those 7 valence or outermost electrons that a chlorine atom will have. Now chlorine only needs 1 more electron in this spot here, okay, in order to fulfill that stable octet. So it's super duper close. So things like chlorine, which have a high number of valence electrons already, are gonna gain, nonmetals are gonna gain electrons in order to fulfill that stable octet. So a chlorine atom will get an electron from somewhere else to kind of go into this spot so that now it has a negative 1 charge, but it also has those 8 valence electrons, okay? So kind of moral of the story here is all of these atoms want to try to act like they're as close to a noble gas as possible with that stable octet. So metals are going to lose valence electrons to achieve that stable octet, and nonmetals are going to tend to gain those electrons in order to achieve that stable octet. Okay, and remembering that these electrons are negatively charged particles, so that if an atom loses or gains them, it's going to affect what the overall charge of that atom is. Okay, so this is kind of what I was just saying before, but metals tend to have 1 to 3 valence electrons, so kind of a lower number of outermost electrons. So they will tend to lose those electrons to complete an octet, okay? Because they only have 1 to 3, so it's kind of easier for them to just like lose them somewhere else, so that they have 8 left over on the outside. Whereas nonmetals are going to tend to have 5 to 7 valence electrons, so that's even closer to 8. So it's much easier for your nonmetals to just kind of gain a few more in order to achieve that octet. So this is a picture here of a Lewis dot structure of a neon atom specifically. So this is what we're going to learn how to draw. But this is for neon. So neon is a noble gas in group 18, and it has 8 valence electrons. Okay, so this is that stable octet, kind of that magic number, that perfect happy number that all atoms want to try to achieve. But neon does that effortlessly because it already is a noble gas and it already has that 8. Okay, so these dots on the outside are representing those 8 valence electrons. Okay, but we'll go over in a sec how to do it. Okay, so there are some exceptions to this octet rule. There's exceptions to everything. But things like hydrogen, lithium, beryllium, and boron, it's possible for them to have 2 valence electrons like helium and be happy. So this is also called the duplet rule, okay, with dupe meaning 2 in this case. Okay, so all atoms don't necessarily need that 8, okay, for the purposes of this class. We're just going to remember that all atoms, most atoms, want to achieve that octet. They want 8 valence electrons. However, it happens that sometimes atoms are happy with 2. Sometimes atoms like to expand and have more than 8, but we're not even going to get into that stuff. Okay, so just remembering that this octet rule, pretty much. Okay, so how do we draw a Lewis dot structure? So what they are is basically a very simple representation of valence shell electrons or outermost electrons in a atom, or we can even draw them for entire molecules. Okay, so this is just an example of oxygen now. So oxygen, you look it up on your periodic table, and there are 6 valence electrons. So if you looked at oxygen and you looked at the electron configuration, you would see that it's a 2-6. So the outermost electrons are going to be how many are in that last shell. Okay, so that's how we know that oxygen has 6 valence electrons. So because oxygen has 6 valence electrons, the Lewis dot is going to have 6 dots. So 1, 2, 3, 4, 5, 6 to show that a neutral oxygen atom with 6 valence electrons is going to have 6 dots around its Lewis dot structure. Okay, so sometimes Lewis dots can be drawn for ions too. So remember, ions are charged atoms that have either gained or lost electrons. Okay, and depending on whether they lost or gained is going to affect what the overall charge is. So if we look at a sodium atom first, sodium is a metal. Again, it has 1 valence electron. So it typically would be written with 1 dot here. If we're just talking about a neutral sodium atom, there's 1 valence electron, so we're just drawing 1 dot for there. So draw the symbol, Na, and the dot. Now, if that sodium atom loses that electron, okay, because it's a metal, it'll lose an electron. In order to kind of achieve that stable octet, it will then turn into a sodium ion with a positive charge. Okay, so when we rewrite it like that, as an ion, because there's a positive 1 charge, that's positive 1 is telling us that 1 electron is lost. And the electron that is always lost is always going to be those valence electrons on the outside, okay? They're closest to the outside, so those are always going to be the ones that are kind of coming and going. Okay, so 1 valence electron is lost because we have a positive 1 charge. So then when we redraw that Lewis dot structure, we just draw it without that valence electron, okay? It went somewhere else. When we draw it for an ion, though, we always represent it with the brackets on the outside and then the charge, okay, just to kind of show that, okay, this is an ion now. It lost an electron. Okay, so we can do a similar thing with a negative ion, so something like chlorine that is a nonmetal and has 7 electrons. Will be written originally like this if it's just a neutral atom. So a Cl for chlorine, and then 1, 2, 3, 4, 5, 6, 7 dots on the outside. If chlorine were to gain an extra electron, it's gaining 1 because it's a nonmetal. Nonmetals will tend to gain them. And then it will turn to a negative 1 ion. Okay, that negative 1 is just telling us that 1 valence electron was gained. Okay, because it is a 1 negative charge. So we gained 1 negatively charged particle or an electron. Okay, so once that happens, you're just going to change your diagram so that, or your structure, so that it added an electron. So this one wasn't here before, but now it is. And that chlorine atom becomes a chlorine ion because it gained that 8th electron that it needed to fulfill its stable octet. And the same thing as before, just draw those brackets around, and then making sure to draw that charge, that -1 charge at the top, to just show that that chlorine ion has gained an electron. Okay, so I'll just show you some examples here, and then I want you to try out the practice that is in your packet. So I'm going to just show you some neutral atoms, and then I'm going to show you how we would do some ions as well. Okay, so let's try out this magnesium first. So if you find a magnesium, you're going to look at your periodic table, find magnesium, and figure out how many valence or outermost electrons it would have. Okay, so magnesium, I look at my periodic table, I look at the electron configuration, and I would see that it has 2 valence electrons. Okay, it's also in group 2, magnesium. So remember that the group numbers are also associated with how many valence electrons the atoms in the elements in that group have. Okay, so magnesium group 2 has 2 valence electrons. Okay, then I'm just going to draw in my valence electrons. So it has 2. I'm just going to draw 2 dots. Okay, so in this case, I'm going to draw 1 and 2. Okay, so when you're drawing these, you want to kind of picture that there's like an imaginary like 4 sides, like this, 1, 2, 3, 4. Okay, so we kind of draw them like nicely around. We don't just randomly place them all over the place. We try to write them in like a little bit neater. Okay, so now let's try oxygen. So oxygen, using our periodic table, we would find that it has 6 valence electrons or outermost electrons. So then we're just going to draw those in. So we would draw our O for oxygen, and then we draw in those electrons. So I always start at the top, and I draw my first 2 paired up next to each other. 1, 2, like that. And then I'll place the rest of them like kind of going in a circle. So I have 1, 2. I'm going to put my third one here, fourth one here, fifth one here, and then my sixth one back over here. Okay. So now what if I wanted to draw one for, say, a magnesium ion? Okay, so if I'm doing one for magnesium ion, magnesium will form a +2 ion. Okay, that just means that magnesium loses 2 electrons. Okay, so all I'm going to do is just not draw these 2 electrons in, right? If I have a +2 charge now, my magnesium atom, neutral atom, became a +2 ion. That means I lost those 2 electrons. So that's it, right? I don't have to draw any dots around. This is going to be how all of your metals look, or every positive ion Lewis dot structure that you draw is going to be shown with no dots because they were lost, right? And that's shown by and demonstrated by that charge. Now, if I did one for a oxygen, which forms a negative charge, so we can do -2, then all that's happening here is -2 ion means that 2 electrons were gained. Okay, so oxygen started out with 6 valence electrons. It's going to become a -2 ion. That means it gains 2 electrons. So we just got to add 2 electrons in those 2 missing spots to fulfill that octet. So we can just draw them in. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so that's all you have to do with that. We're just going to do neutral atoms, and then we'll also do a little bit more practice with the ions as well. But all you got to do is write down the symbol, look at your periodic table to find how many valence electrons that atom has, and then you just draw the dots around the symbol, but just trying to keep them kind of neat. So if you think of the letter as being like, these are like 4 sides, almost like a square. Okay, and then you can kind of neatly put those circles around. Okay, 2 on each side they would go. Okay.